Okay.
There we go. It's okay. Sorry. We're
All
gonna
good.
go back for like 2 seconds.
Yeah, so once again, first part of this lecture is PID. Then the second part, we're going to be going over the most important parts of the capstone. So yeah, so for the control system, that's basically, again, just kind of an organized pathway that you can make a system follow. In this case, your Arduino code is what represents that actual system. It's your car, so you'll be programming it to do one of two things, either follow your hand or follow the wall, right? So the important thing here is that you want it to maintain kind of a certain distance away from either your hand or the wall. And you want to think about how exactly you would go about tracking that. You'll need some sort of sensor, and then you need a way to keep track of how that distance changes, right? So that's your error. Now the question that you want to answer here is how do you actually account for that error when you're tracking a reference, right? If you're constantly measuring the distance that your car is from your hand, how do you adjust where your car is to follow your hand or the wall? Um, so this is where PID comes in. That stands for proportional integral derivative. These are just three different types of controllers that you want to use. Once again, if you're in EC3, all of this will probably be familiar to you. But yeah, this is essentially just used to reduce or smoothen kind of these oscillations when you're correcting a system, by which we mean when you're getting your system, your car in both cases, to track something, right? Either your hand, the wall, or the track itself. Then the PID controllers, each of the three I mentioned, uses a slightly different method to actually keep track of how your error is changing, keeps track of different parts of it, and then self-corrects. So we're going to go over the three types. The first one here is easiest to understand, right? So here we have a little diagram, right? So you see that the car goes below the track first, and then it goes above, meaning too far to the right or too far to the left. So here, our error is exactly the distance between where your car is and the track itself, right? Now, you know that if you're way too far to the left, then you probably have to self-correct even more than if you're just slightly left of the track. That's what the proportional controller is, right? Because the signal that you put in, how you make your car, how far to the right you make your car go, is based exactly on how far away your car is from the track. Does that make sense? Now, one question that we have to kind of ask ourselves with the proportional controller is it possible to achieve zero steady state error? What that means is that in the long run, if you let this car go and you start it off slightly to the right of the track, will it eventually settle and be exactly on the track? Hmm. Is it, how do we, okay. I guess, well, okay, the answer is no. Um, not in most cases, I guess. And the reason is if you think about what happens when your car gets close to the track, right? Imagine it's like, let's say a centimeter, an inch too far. Then it says, okay, I need to move to the right. But then what happens in the next second? It crosses over and moves to the right. It overshoots the track. And then the same exact process will repeat, right? Because then the car says, oh, I need to correct back by going left. So it goes left and then it overshoots once again, and you end up with some oscillation. So now we have to think about, can we actually get rid of that oscillation, have the car move towards the track and then follow it exactly? So that's where the next controller comes in. So that's the derivative controller. Here we pay attention not only to what our error actually is, but how it changes with time, right? So we want to really quickly, there's something I need to mention about each of these. Yeah, so when we say you scale your error, right? That doesn't mean necessarily that you exactly take how much distance you are and then translate that. You need to map it to some value, right? For example, let's say that your car, you can move your car slightly to the right by like, I don't know, to make this more concrete, you can make it move 1 inch per second to the right, right? And that'll be based on if your car's like, I don't know, 6 inches to the left or something. So it'll move faster towards the track if you're further away. That's what we mean when we say that you're scaling your error and then using that to feed back into your car. So moving back to the derivative controller, if we see that our car is moving further away from the track, meaning we're not just following whether the car is to the left or to the right, but we're actually seeing if it's moving further away or closer to the track, then we adjust the car's motion accordingly, right? So if we see that we're approaching the track, meaning we're too far to the left and we're gradually moving toward it, then we say, okay, the car can slow down. It doesn't need to go way too far to the right. And eventually you can imagine that I've been like doing these motions with my hands. I realize you can't really see. it'll settle in and meet the track eventually, right? Um, One drawback with the derivative controller is that it's sensitive to noise and sharp changes. What we mean is that if your car suddenly, let's say for whatever reason, it gets some measurement wrong or something, and you go from your right on the track to, for some reason, it tells you that you are an entire foot too far to the left, right? Then your car will say, oh, shoot, I need to move way to the right, like really fast. And so in that way, if your measurements are actually changing super fast, right? Then your car will correct accordingly. And that's bad because it'll probably result in your car moving off the track, as you can imagine. So that's the con to the derivative controller. Recall that for the proportional controller, the drawback here was that it doesn't achieve zero steady state error, right? There will always be some form of oscillation if there is initial error to begin with, if your car starts off not on the track.
And one thing of note is that we need the derivative error when using our when creating our capstone car, because the motors that we use aren't perfect, and so there's no guarantee that whenever the car is moving forward that the motors are like basically driving, or sorry, that the our integrated circuit that we're going to use is driving the motors at the exact same speed, because there might be differences in the motors that makes it like a little skewed. And so in that sense, there's no guarantee that we'll actually be able to put the car straight, like to go straight in a line. And so in that sense, we have to like use derivative to smooth in its trajectory.
Mm-hmm. That's right. One way that you can actually think about how you might go about smoothing this kind of error is by keeping track of not just the last, um, again, to make this concrete, let's say that the way that you actually keep track of your error, right, is that you know exactly how far your car is away from the track at all times. 1 second it's on the track, next second it's 1 inch to the right, etc. Right? So instead of just keeping track of the last measurement, you keep track of the last few and then take an average. That way, if you go 1 inch left, 1 inch left, 5 inches left, it's not going to say five, it's gonna, it's gonna be closer to what the average measurement is. And that way your controller becomes less sensitive to these sharp changes, which is for the better. But if your car does obviously move closer to the track, it'll still be able to track that as well because the average distance will drop over time. And so your car will be able to adjust. So far, does that make sense? You can respond in chat or I guess thumbs up, something. Okay, we got one chat message, two. All right, perfect.
Yay, let's go. Okay.
Yeah. So now we have the integral controller. This is the last of the controllers, and I don't think you need to implement this for your project. Basically, what the integral controller does is pretty much by taking all of your errors over time and then keeping track of that. The reason why this is useful is because it'll be able to tell you whether you have kind of a constant, let's say you're constantly, like if your car consistently moves to the left, right? And so it's been off the track for a bit, the integral controller will catch that, right? Because you have some constant error over a lot of time. And so because of that, you'll be able to keep track of exactly how much your car has deviated from the track over a bunch of time and then be able to adjust in a different way than the proportional controller and the derivative controller, which both basically just look at what your car is doing in the current moment, right? So the drawback here is that the integral controller responds more slowly to error. I think this makes sense because it needs time to actually, again, accumulate your car's measurements and see exactly where it is over a lot of time. But this is another way that you can reduce your overall error to zero.
And just for like a quick recap, of, well, this is like a summary, but in order to like try to like ground what we're talking about, essentially is that we're gonna have measurements of when your car is going, and then you're gonna somehow measure error. That error is dependent on your car and like what it's doing, but generally it's gonna be like, oh, if it's like off from doing certain thing, and then for that error value, you're gonna either gonna proportionally changing how you're moving, or you're gonna like calculate a derivative of the previous errors, or you're gonna take like an integral, basically just like adding all the previous errors you've ever had and changing things based on that. So basically, you have your error and you just do separate calculations for each controller, and then you change, for example, for our cars, it's gonna be how fast we're going, or like either how fast you're going or what direction you're going in. And so let's say you know that you're supposed to like you don't need to go as like your error is telling you that your error is telling the car or you, I guess, that you're too close to something. So then proportionally it would make it like slower, I guess. That sounds kind of confusing, but we have some like pseudocode that
Mhm.
makes it a little less confusing later.
Yeah, we'll explain the mechanism by which you actually kind of track these measurements. Like we have the code for that, so we will probably provide you with the skeleton. We'll explain exactly how that's done. And one quick thing that I also want to mention is that for the derivative controller, these are we've kind of introduced these in the context of, something continuous, right? But obviously when you're doing your Arduino measurements, you're taking measurements discretely. So all the derivative means in that case is a subtraction. You take successive differences of your errors, right? So you just subtract one measurement from the next, and etc. That's all that means.
Yep. Okay. So we have finished the PID, which is kind of like the coding part of the capstone, and now we're going to get more into the actual capstone, which is pretty important. People said that they enjoyed like seeing, or not seeing, but people enjoyed like us going over the specs a little bit. So we're gonna basically be going over the entire spec, but it also helps just explain what the capstone is. If you have any questions at all times, remember you can either say something out loud or type in chat. But our capstone is going to use a couple of different components in the ops kit that we haven't used before, as well as a sorry, as well as a new integrated circuit that you'll be picking up in the lab, hopefully sometime next week, assuming that the lab opens up. But on the note, if the lab doesn't open up and classes are still online, we'll be opening up the lab like for certain periods of time during the week in which you guys can come and pick up your parts. The lab won't be open to like everyone, but like if you knock on the door, we'll open it for you and give you your parts. Because we don't want to stop all ops things. But yeah, so let's get into the capstone. So, ring ring. Your task here is to become Elon Musk and create an autonomous vehicle. Um, Essentially, it's called Carduino because car and Arduino, Carduino. And so we have the spec linked somewhere.
Do you want me to post a link in chat?
It's here.
Chat, not Discord.
Discord. I can put it in chat. How do I get the link? Copy link.
Oh yeah, I'll also drop the link in links.
It's there. If it's in chat, oh, I just opened it on accident. Oh God. Oh God. Get me out. Wait. Okay. Sorry. Okay, we're back. Okay. Autopilot mode. So it's gonna be a self-driving car in the sense you like set it on the ground and it'll do things. But you can choose which of two different routes you can go down. So the capstone will be a partner or triple trio trio project. You can also do it by yourself if you really want to. You don't need to. You can choose how you want to work in the for the capstone. It doesn't require more than one person though, because all the parts you can just use like from your own ops kit. It doesn't require two Arduinos or anything, but we recommend doing it in partner project or a trio because there's a lot more work. And it's good to bounce ideas off of your fellow ops students. But the two autopilot modes are we have for the Carduino is the hand following car and the wall following car. And so this is generally what it looks like. So for the hand following car, essentially the car is kind of like really wide. As you can see, it's like this is kind of the front of it and the back of it is like just the back, like the other side of the breadboard. And what happens is that using the sensor, this like googly eye looking thing, the sensor will read how far something is away in front of it. And then based on that, it will either move forwards or backwards. And so it's an ultrasonic sensor called the HCSR04. That's not really important, but so that's one option. And then the second option is wall following, which could looks kind of something kind of like this, in which you in which the car is going to be going forwards parallel to a wall, and then it'll move when it senses it needs to take a turn, like as in corners, or the wall isn't like completely like, or like it's straight, but like the wall, it isn't completely parallel to the wall, it'll redirect to make sure that's following the wall, like wall following. And so with this situation, the sensor will face the, like, instead of facing forward, it'll face the sides of the car. And so I think in this picture, the sensor is like behind here or something, and it's facing the other side, but it won't be facing forward. And so you and your partner, or two partners, or you're by yourself, you can choose which Arduino to create. But both use basically like the same mechanisms and don't really differ very much in terms of the actual project. So I don't think there's one that's necessarily easier. You can just choose whichever one you want. Okay, so the ultrasonic sensor is a part that we have in our kits, the HCSR04, and it looks like this on the bottom right. And essentially how the HCSR04, sorry, how the sensor works is that it has this trig and this echo pin. And what it means is that the trigger, like when you have to connect both the trig and the echo pins of the sensor to a pin on your Arduino. And then whenever you hold the trig low, as in like input a low signal to the trig, it tells the sensor that it's going to be reading, it tells the sensor to start reading in values. And so what the sensor will do is, using echo, it will first send off an ultrasonic like wave. It'll like send out a wave, and then it'll wait a certain distance until it receives that wave back. And so it will be able to determine how far away something is based on how long it takes for that wave to come back. And if it doesn't come back within a certain amount of time, we're doing an ops lecture. Sorry. And so if the sensor does not receive the ultrasonic wave within a certain time, it times out and just like returns some maximum value.
Yeah.
Yeah. And so this is how we measure like the basics of how far something is. We can use the ultrasonic sensor, and we'll be using this sensor to do like the main axis of the car. So like forward, basically. Or forward if for the hand following, or to the side for the wall following. And we have a built-in function within Arduino called pulse in, and you can use this pulse in function to actually, that'll do the easy measurement of how far something is using the ultrasonic sensor. And we won't tell you everything of how this does because you can read the documentation for it, and that's a little challenge for you guys. Anything you want to say?
No, not really. Yeah, that's exactly how it works. You'll measure the time pretty much, and then you'll be able to figure out the distance from there.
Okay, any questions from here? Okay. Okay, now we have H bridges, and this looks kind of complicated, but do not worry because you don't even understand it to actually use the H bridge. So like the other integrated circuits that we've used, like the 555 timer or the
Yeah, that's cool.
that's cool.
You probably like restart the meeting or something if
Well, so I don't have Zoom Pro, so the free meeting will end in 10 minutes. And I don't know what to do about that, so let's just speed run. Okay, so basically, the H-bridge is another type of integrated circuit that we have that we're going to be using, and you have to pick it up. Sorry, the H-bridge is not in, it is a integrated circuit technically. It's just like a circuit. And our integrated circuit is called the L293D, which has two of these circuits inside of it. And essentially, the H-bridge allows us to control the direction of a motor with one power source. It's like effectively, or not effectively, it uses transistors as switches, and we learned a lot about transistors in the lecture 2 lectures ago, and also talked about it during power ups. So some of you might be very familiar with transistors at this point. And this is kind of a overview of how the um, integrated circuit works. Is that when you have these different 4 pins, IN1, IN3, IN2, IN4, and they correspond to the 2 motors we will be using for our car. And each pair, as in IN1, IN2, and then IN3, IN4, as in 1 and 2 is a pair, then 3 and 4 is a pair, each pair corresponds to 1 motor. And you can change whether you drive each one high or low. And the combination of the two will tell the motors whether to go forwards, backwards, or stop. And so as you can see here, when IN1 and IN2 are both low or both high, the motor knows not to go at all. While if you have IN1 as high and then IN2 as low, it'll go forward, and then the opposite is when it goes backwards. And so this is the integrated circuit, the L293D. It has 16 whole pins, so it's kind of insane wiring it, but hopefully you don't get too confused. Yeah. Anything else?
Yeah, I mean, I think it'll probably be easier to make sense of this once you actually start working on the capstone. Yeah, I recommend probably like get your motors and wire like we'll mention this later on, but you have to solder wires to your motors. Get that done first, and then probably like put together your car from the bottom up. So like attach the wheels and
Yeah.
then do the rest of the wiring after. I
We'll
think that's
get
probably easiest.
into that like in a second.
Yeah.
Here's more about H bridges. Not super important, I guess, to understand. Okay. And then for the actual pins, there are 16 total pins, as we mentioned. First of all, there are 4 for ground. So you just connect all those to ground, which is pretty simple. And then there's 2 for power. The 16 pin goes to 5 volts, while the 8 pin goes to V in. And then there's output, in which these ones you connect to your Arduino. There's direction. These ones are connected to the different motors. You'll have IN1 and 2 into one motor, and then 3 and 4 into the other one. And then you have speed. And so the spec will go a little bit more into this. But you don't really need to you don't really sorry.
We have a chart for all this in the spec themselves.
Yeah.
So yeah.
We'll go into that in like literally 2 seconds.
Yeah.
But we have this fun graphic. You'll see all the different things that you'll be using in your capstone. So you have the sensor, it'll go here, or somewhere wherever you want to place it. You'll have your your 2 H bridges and the integrated circuit somewhere here, your Arduino somewhere, your batteries, your motors, all these cool things. Okay, so here is a quick summary of the spec. So the first part of the spec goes into how to actually wire your L293D, and it looks pretty long and complicated. And I also created this like kind of insane diagram of how to do it, like with all these different like connections. I spent some time on that, so I hope you appreciate it. But also, I understand if you don't understand it because it's really confusing, but that's okay. It's basically like doing the exact same thing that I just said 2 seconds ago, in which you have 4 to ground. You see, have like the 4 in the middle to ground. You'll have pin 8 to V in, pin 16 to V 5 volts, and then you have 1 and 9 to 2 different PWM pins, which control your speed, and then you'll have 4 pins going to your motors. And then lastly, 4 for direction inputs. You can see at the bottom right, which connect to digital pins. So the writing here describes all of that, and it should be pretty intuitive and pretty easy to understand. But if you have questions, of course, you guys can ask us. But this here is an example of how you can do it, if you want to like zoom in and figure that out when you're like building your capstone yourself. Yeah. And then next in the spec will be your motors. This is actually pretty important because your motors, which will be connected to the wheels, the motors don't come. The motors might come with wires, but they also might not. It depends.
We might have some from last year that are already
soldered. We have some motors that have wires. We have some motors that don't have wires, and for the ones that don't, you actually have to solder them. So we haven't done any soldering this entire year in ops, but this is your chance to, if you would like to. or you might have to. And so we're gonna have some demonstrations in the work sessions. The first one is next Thursday on how to solder, and we will make sure to tell you how to be very safe because soldering can go very bad if you are unsafe about it. But we're gonna have some spool of wire, which you have to cut yourself, and then you can use that to connect your wires to your L293D. And we also have some sample code within the spec, which also pasted here, in which it shows you how to set up your motors. This is pretty useful because it's kind of confusing at first how to actually do it. And so we hope that this like kind of summary helps people approach it a little easier because it's overwhelming at first. But yeah, using this like testing or like using this test code like kind of jumpstarts you into doing a lot of what you need to do. Yeah. And then next we have to actually build the car. And so as we mentioned earlier, we have the wall following car and then the hand following car. Both of them will need a ball swivel. We'll give you like those parts of ball swivel to make the entire car balance. And both of them will use the ultrasonic sensor, but the only difference in the wall following car is that it'll also use IR. Remember for project 6, we use the IR emitter and receiver pairs, and we'll be also using those. You'll also be using those if you do the wall following car because that is what allows you to track the distance you are from on all axes, because then using the IR sensor on like the other side of your Arduino or like, the other side of your car, you can know when to turn, not only just like stay straight. Yeah. And then the next part is the actual sensors. So first is the HCSR05. And so here's like a very simple pinout. It doesn't require many pins, only 4 pins. 1 to power, 1 to ground, and then 2 digital pins. And as we mentioned, for the ultrasonic sensor, you'll have to be using trig, where you pull it down, and then you use echo to actually read in the values. And as we mentioned, there is the pulse in function that helps you do this. And then secondly, we have the IR emitter and receiver pair. This exact same thing as in project 6. So if you need any help with that, you can reference the spec for project 6. But an example of how this would be done is that on the right, you see a picture in which there is the IR receiver and then a red LED, because you can substitute it for the emitter if the emitter is faulty. And so whenever this end of the car gets close to a wall, the red LED will emit more light and it'll bounce back to the emitter. And so the emitter will read that and notice that the car is close to a wall and then correspondingly change how the car is moving. So hopefully that intuition makes sense. Okay. Okay, so we have 1 minute. I don't think we can like finish in 1 minute. So what should we do?
Do you want to try restarting the meeting? I mean, I'm pretty sure you should be able to, right?
Yeah, okay, we're gonna restart.
Yeah.
You
just hop back on.
Yeah, just please hop back on
Yeah.
to the Zoom and like just like right now. Okay, see you soon. So now we're on.
Yeah, so sorry about the slight hiccup, but yeah, we're back right away. Let me share screen here. Okay. Where were we? Here, right?
Yeah. Can everyone see?
Y'all can hear us okay, right?
Yeah.
Okay.
Cool.
Yeah. So I guess I can take this part. So yeah, going on to the PID controller project, we can talk about this a little bit in greater detail now that you know how your sensor works. So again, yeah, the basic idea is that you're taking what the pulse in function will essentially tell you is how much time has elapsed between when you send out the pulse and when you receive it, right? So you can use that to calculate the distance between your hand and the target, between the car and the target, right? So you'll have to finagle with it to see exactly what a
so
target
pretty much
distance.
like this is so funny to me. So pretty much on Sunday, the guys that did
Oh, oops. Anyways, yeah. So, when what was I saying? Oh yeah. So you'll need to actually experiment with it to see what would be a good distance that you want to have, right? So one that you can reliably follow with your car. based on the type of car that you'll be using, either the hand following or the wall following car, your code might be slightly different, but the general idea is exactly the same, where you'll want to either turn or speed up or slow down your car based on how far away your car is, right? So here we have a bit of sample code. I don't remember if the skeleton that we provide looks something like this. Maybe it does, maybe it doesn't. You can use this as reference. Let's talk about what PID kind of looks like in code. So here we just have, you'll need a bunch of setup pins, obviously, for your motors and stuff, so that we haven't included. Okay.
Recording.
Yeah.
Okay. Sounds good. Sorry.
All right. So yeah, the KD and KP are just constants here. You'll need to adjust those based on exactly how fast your motors will actually go. But basically the idea here, right, is that you have some normal speed for your car, indicated here very helpfully by the name normal speed. And let's say that your hand moves in front of the car, right, too far ahead, by which I mean, then your air might be, let's say, positive, right? And so you want your car to speed up to catch up to your hand. That's when you add to the speed of the motors. And then obviously it's different when you if you move your hand closer, right? So your car might slow down and eventually back up. So those are all parameters that you'll need to kind of set up. And again, you'll need to kind of experiment with it to see what each of the thresholds should be, what your KD and KP will be. They'll be different for everyone. So yeah.
Yeah, and so just like point out what is happening here, I guess. Or just some things. I didn't or
Do you want to use the laser thing?
the laser?
Yeah.
Wait, where's the laser?
Well, it's like a slideshow option, right? Hold on.
Oh, that's what you meant.
There's
Yeah.
a pen. Try this.
Ooh. Does it stay there?
I guess.
Oh, you can erase it. Oh, no. Okay, we're going to laser. Sorry. Anyway, here. Okay, so I wrote the pseudocode like yeah. One thing is that this should be IN 1 and IN 2. I will change the slides to reflect the change it should be. So because EN 1 and EN 2 is what dictates whether the motors are in like backwards or forwards mode. So yeah, it should be IN 1 and IN 2. That will change the actual speed. But anyway. And so yeah, we have our normal speed and then we change it based on the error value. But as you can notice for KD, which is the derivative, it's not going to be the same as KP. For KP, it just simply you just simply add, and the error will basically determine whether it's going to be positive or negative. So let's say the error is positive, you can change like how you record the error, I guess, or how you calculate the error. But the error, like for intuitively, let's say the error is positive, that means you're too far away, and so you need to speed up, and so then you would add, right? Or you're gonna add no matter what. But then let's say the error is negative, meaning you're too close. That makes it so you subtract from the normal speed, and so that will make it slow down. For the KD, which is the constant for the derivative controller, you're gonna have to calculate it. You're gonna multiply it by not just the error, because it's not the proportional constant, it's the derivative. Yeah, it's a derivative constant. And so we're not going to tell you exactly how to do it, or as in like we're not going to give you code how to do it exactly, because we'd like you to figure that out. But for the derivative, you want to basically find the change in error and adjust the speed corresponding to that. And so I didn't write exactly how to do that, but you can figure it out. But this is like essentially the very basics of how your code is going to look. It'll be a little more complicated than that, because when you're going backwards or forwards, you have to change the EN modes. And then also you might want to turn if you're doing the wall following car and all these different things. But generally, this is kind of like the very basics of how your project will look. So does this make sense? We have a chat message. Oops. We're good. Okay. So lastly, we have some important notes. So as we mentioned a little earlier, is that we have to solder our motors. We're going to have spool to give you. You'll find that in the lab. And so in order to actually do the soldering, you do have to be in the lab, because you don't have a soldering iron at home, I assume. That'd be cool if you did, but I'm going to assume you don't. So that requires to be in the lab. Also, not most, but a lot of the parts you're going to be using in the project including the L293D and the motors and the wheels and ball swivels. Yeah, all of those things are gonna be required to be returned after you complete the capstone. So you cannot keep those, unfortunately. And then the last two things is that there is a not so secret option 3 for the capstone, in which you can use processing and your HCO5 to make it a remote controlled car. If you weren't able to get the HCO5 project to work, like, don't even probably consider this, because I think it'd be a big pain. But it is pretty cool in which you create a remote controlled car. I did that last year and it was a lot of fun. It was a lot of pain trying to get it to work, but it was pretty cool in the end. But not the caveat, but like the important part about this is that if you successfully get this to work as an additional thing you do, in addition to either the hand following or the wall following car, as in you do both. You do either hand following and wall following plus the remote controlled car. You can essentially like remove a incomplete on one of your past projects, and like you can like basically make that up. So if you want to do that, that's pretty cool. It's also like a fun challenge. And then lastly, you have to have a team, or you don't have to, but we highly recommend having a team for your project. So make teams of 2 to 3 of your fellow ops people, and you will have to come into the lab to pick up your parts in the upcoming week. And we posted our lab hours in the announcements, I think like a couple weeks ago, but we'll also like pin it or something. But we're in the lab Tuesday, Thursday mornings / afternoons. You can find us pretty reliably if you would like to pick it up outside of ops time. And also, we will have plenty of work sessions. Yep. And so that's generally it. That's the last slide. So any questions from here? Okay, so that concludes our last, oh God. That concludes our last lecture. We're sorry to have it over Zoom. It'd be a lot nicer of a send-off if it was in person. But we'll still see you guys for work sessions in the upcoming week. So it's not, ops isn't over yet, but it is the last like formal event, I guess. So thank you so much for coming, and we had a really great year teaching you guys and being your ops leads and being able to give you this opportunity. It was a very, I don't know, fun and rewarding time. And so thank you all for making it such an amazing experience.
Yeah, we had a lot of fun during all of these lectures, and we really wish we could give you like a proper send-off given everything that's happening on campus. Thank you for coming out this lecture and the last 9 lectures, work sessions and stuff. Yeah.
Okay. Thank you
Yes,
so
that's
much.
that.
Bye-bye. See you next week, hopefully. Bye-bye. Okay. Do we just go?
I guess. All right.
Okay.
Yeah.
Hi, Wyatt.
Yo.
Oh no.
All right.
Never mind. Never mind. Wait. No, don't leave. Okay, wait.
Oh.